Okay, so this is lab 1, composition of concurrent forces. This is basically just adding vectors. So we're going to add vectors in 3 ways. We're going to add vectors graphically, so actually drawing the vector out and having a scale for the length of the vector and adding up vectors head to tail, okay? Then we'll do it analytically, which is most of the time that's how you're going to be from here on out. That's how you're going to be adding vectors, is analytically. So we'll break the vectors up into components, and we'll add the components that's in component form. Then we will put everything back in polar form where we have a magnitude and an angle. And then for the experiment, we've got the force table, which we'll show you in a minute, and we will add the vectors by actually building the vectors on the force table. And we'll check what we've done. So the first way that I'm going to do it is graphically. And if you look on your paper that you have group 1 and group 2. So I'm going to do group 1, set 1. So there are 3 vectors there. There's vector A, vector B, and vector C. You're given a magnitude and an angle. That angle is always measured from the positive x-axis. So vector A, I'm doing group 1, set 1. So vector A, that's a bad marker. Okay. So vector A, and if I write that little hat over the letter, that means vector, okay? Vector A is 200, and the magnitude that we're going to use the units will be in grams, but everything we're going to do will be in grams. I'm not going to put the grams right there. I'm just going to say 200 at 0 degrees. Vector B is equal to 100 at 70 degrees. And vector C is equal to 100 at 135 degrees. Okay, so I'm going to set up a scale for these vectors. And you always want to set up some kind of scale that's going to fit what you have to work with. So I've got this old little, it's called a gravity protractor. I like to call it the anglometer. That's not the real name. But anyway, so it's in inches. So I'm going to set up a scale in inches. So I'm going to have 10, let's see, I'm going to have 20 grams. So 20, I guess I will put the grams here. 20 grams is equal to 1 inch. Okay, so 10 inches would be 200 grams. 5 inches would be 100, and so forth. Okay? So I'm going to use this to draw out the vectors. So I'll put vector A in purple. So I've got vector A is 200 at 0 degrees, so I'm here at 0 degrees. So 200 will give me 10 inches. Whoops. Okay. All right, let's see how well I can do this. All right, that's pretty good. Okay. So that's vector A. When adding vectors graphically, you put the tail of one vector, or the vector that you want to add to the first vector, you put the tail of that vector onto the head of the first vector. And you always measure the angles from the positive x-axis, so from that horizontal. Don't measure your angle based on the previous vector. Every vector you draw, you measure that angle from that positive x-axis, okay? So vector B, I'm going to attach it to vector A. It's 100 at 70 degrees, so that's 5 inches. at 70 degrees, and I'm going to put vector B in red. So let's see, 70, is that about right? Okay, somewhere right there. All right. Okay. So that's vector B. All right. Vector C. I'm going to put the tail of vector C onto the head of vector B. And it's at 135. So that's 45 degrees past 90, because this thing goes from 90 to 90. So I'll have to figure that out. Let's put it in black. Okay, so 45. All right. 45 degrees. And it's the same length as vector B because it's 100. So that's 5 inches. All right, right about there. All right, so there's vector C. So that's A plus B plus C. Then to find the resultant, you simply connect the tail of vector A to the head of vector C, and that's the resultant. So I'll do that. I'll make it blue. Then once I measure the resultant vector, I can figure out, using my scale, I can figure out the magnitude of the resultant. Okay, so here we go. Not bad. All right, so that is what we'll call R. That's the resultant vector. So I know you didn't see me, but while I had this up here, that vector measures about 11.5 inches. So our magnitude, if I write it like this, that means magnitude. This also means magnitude. If I write it without the little arrow, that's just the magnitude of the vector. So our magnitude is equal to 11.5 inches, and that is equal to, if I take 11.5 times 20, that's 230, 240? What is that? No. It's 220. What's 11.5 times 20? I can figure that out pretty easily. That's 230. 230 grams. Yeah. Okay. What about the angle? So I'm going to call the angle theta resultant. Okay, so let me measure the angle. And I'm going to put this right on 0. And all right, I'm getting 46 degrees. So theta R is 46 degrees. Okay, to report that as a vector in polar form, then I would report it just like I did these. R is equal to 230 at 46 degrees. Okay? Okay, so this is where the audio begins to give us trouble, and from here on out, I will narrate what I did. It'll take just a minute to get the narration started, so give it just a second, and hopefully I can explain what's going on Some of this is okay, but some of it's not. So here I'm just starting to write down and add the components for each vector. Okay, so this notation I'm using is that's the x component of vector A. That's the magnitude of A times the cosine of the angle from the positive x-axis. AY is magnitude A times sine theta. Okay, so I'm going to go ahead and write the numbers in. So this is 200 cosine 0 degrees. Well, cosine of 0 degrees is 1. This is 200. And you can see that's vector A that has no magnitude in the y direction. All its magnitude is in the x direction. So, I mean, I automatically know that this component is 0, but I'm going to go ahead and write it down anyway. This is 200 sine 0 degrees. Sine of 0 is 0, so this is 0. Vector B. Bx is equal to b cosine theta, and that is equal to 100 cosine 70 degrees. By, which is the y component of b, is b sine theta, and that's equal to 100 sine 70 degrees. And it just so happens that I have those values here. This is 34.20, and the y component is 93.97. Now for C, Cx is equal to C, magnitude C, cosine theta. Kind of redundant, but oh well. That is 100 cosine 135 degrees. Okay, so this is calculating the components of C. That's Cx and Cy. So cosine of 135 is something in the second quadrant, so I would expect that Cx is going to be negative. So sine is going to be positive. So here I'm writing down the values for cosine 100 cosine 135, which is negative 70.71, and Cy is equal to positive 70.71. Okay, so now we're going to construct the resultant vector, and that just amounts to adding up the components. So Rx is equal to Ax plus Bx plus Cx. So we have those values over here, which is 200 plus 34.20 minus 70.71. So I'm writing that down over here. And the sum of those three is 163.49. So that's the component of the resultant in the x direction. Then you do the same thing with the y direction. AY is 0, BY is 93.97, CY is 70.71. And that gives you a total of 164.68. So now we've got to reconstruct that polar form of the resultant vector. And I'll use Pythagoras to do that. So r, which is the magnitude of the resultant vector, simply the sum of the squares of the components, take the square root. So that's what I'm doing now. So that's 163.49 squared. That's the resultant in the x direction. And 164.68 squared, that's the resultant in the y direction. And now that gives you 232.05 for the magnitude of the resultant. It's pretty close to what I got by doing it graphically. Not bad. Now for the angle, that's the arctangent of ry over rx. So if you're in the first quadrant, it's no problem because you have a positive x component and a positive y component. So I don't have to add 180 to anything. That's what I'm showing here, that if you're in the second or third quadrant, you have to add 180 degrees to the result. So okay, so that's the y component, that's the x component. So y over x, and then I'm going to take the inverse tangent. So theta sub r is equal to the inverse tangent of 164.68 divided by 163.49. And put that in the calculator, that comes out to 45.21 degrees. So the graphical method gave me 46 degrees. That's pretty close, not bad. Okay, so next we're going to go over to the force table and set this up and see if we can determine the resultant experimentally with masses and true forces. Experimental part. So we're going to actually build these vectors on the force table. Let me show you what the force table looks like. Okay, so the force table has markings on it that give you the angle. It goes from 0, 90, 180, 270. So there's 90, 180, 270, and back around to 0 or 360 degrees. The hangers themselves are worth 50 grams. So when we add a mass to the little hangers, let's say we want 200 grams, then we would just add 150 to the hanger. So what you want to do is you want to balance it where the little peg right there and the ring, or the ring is centered right there on the little peg, okay? So what I'm going to do is I'm going to add masses to the hangers that are equivalent to the vectors that we were looking at. So at 0, we need 200. So I added 150 to the 0. Now moving that around to 70 degrees, so we had 100 at 70. So I'm adding 50 because the hanger's already worth 50. Then over here, I got to go back to 135, and we had 100 at 135, so I'm going to add a 50 to that. That makes 100. So now I have the three vectors set up. I have the 200 at 0, the 100 at 70, and the 100 at 135. So what I'm doing here is I'm trying to get a feel for where that resultant is going to end up. So I'm using just the tension in the string to produce the force, and I'm moving it around to see where I get equilibrium. What you have to remember is on this force table that what we're setting up here is the negative of that resultant that we calculated, because we've got to balance that resultant, okay? So that's what I'm doing here. I'm balancing that resultant. So it's the resultant vector plus about 100, well, it should be plus 180 degrees. So now I'm moving the little pulley over there to where I think I found that angle for the resultant. And then once I've got it there, I'll go ahead and add the masses that should balance those three forces on the other side. So it should be about 200, what did we calculate? 232. So I'm adding 230 at this point. And now it's pretty close. I'm moving it around to see what, just fine tuning it a little bit. And let's see what happens here. Okay, so it looks like it's very, very close. I think I've got 230 on there, but I need a little bit more mass. So I'm going to add a penny, I think. A penny's about 2.5 grams. So there's a penny. Still probably needs a little more, so I'll get a 5 gram. I think takes a second, but we go over and get a 5 gram mass to go on there. So that'll bump it up to about 235, and I think it comes out pretty well balanced at 235. So there's the little 5 gram mass, and I'm going to add that. Okay, that's pretty good. After the 5 gram mass is added, it's pretty well balanced. So 235. So experimentally, I mean, that's 1%, 2% difference than what we had actually calculated. This experiment. So when we talk about sources of uncertainty, I always want to think about things in the experimental setup that anyone would have to deal with if they were doing the experiment. And also things that you could quantify. All right, so several sources of uncertainty in the experiment. There's friction in the pulleys. There's maybe the table is a little bit unlevel, the force table. We didn't calibrate the masses. We're assuming that the mass we're assuming that the masses are correct. There's several other things that you could think about. Maybe the string's not hanging perfectly straight. And also another thing is what I like to call fineness of scale on the force table. About the best you can do is maybe plus or minus a half a degree. The little marks that are between the angles are 1 degree measure. Each little mark is 1 degree. So maybe you can judge a half a degree. Just make sure that when you talk about uncertainty, you're thinking about these things in the experimental setup, that if you had to quantify, you could. If anyone were doing the experiment, they would have to deal with these same uncertainties. Human error is not one of them.